vector fields are things that I think are kind of fun to experiment with and try to get insight with through these experimentations. And how do you experiment in math? Often with the computer, like Mathematica. Let's consider what happens with a vector field of this form. It's a fairly simple form for a vector field. Fairly simple formula. A and B are constants. X and Y are the variables. Before I use VectorPlot to plot these things, let's compute what the curl and the divergence are. Now remember, this is a two-dimensional vector field. If we were going to use the curl based on its full formula, we'd have to convert it to a three-dimensional vector field by adding a comma 0 here before taking a cross product. However, and that would be, technically the curl would be a three-dimensional vector. I don't know if you remember from the reading, but for a two-dimensional vector field like this, say this is the plane, the XY plane, the curl would point in the Z direction as a three-dimensional vector. However, the X and Y components of the curl are 0 in that case. So effectively, we can just focus on the third component. As far as the formula in the book goes, we can just focus on what you could call the scalar curl. That formula right there, nx minus my. Derivative of the second component with respect to the first variable minus the derivative of the first component with respect to the second variable is a long-winded but informative way to say that. So this is the m function, and this is the n function. The curl of f is n, again, nx minus my. That's, in this case, 0 minus 0, 0. The curl of any such vector field is 0. Does that make sense conceptually if we draw pictures? Let's see what happens. I could use VectorPlot. I also could put that inside Manipulate to allow myself to change A and B. For any fixed value of A and B, we get one vector field. But if I allow myself to change A and B, then we get different vector fields. The syntax inside VectorPlot for this example would be A times X, comma B times Y. Then I give a plotting window for X and Y, like -5 to 5. Outside the VectorPlot, but inside the Manipulate, I need to allow myself to change A and B. And if I want to say start A and B both at 1 and allow myself to make them bigger or smaller, including into negative values, the syntax turns out to be like this. That will start A at a value of 1, but it will allow me to make it down to -5 or up to +5. And similar syntax will allow B to start at -1, but go as low as -5 or as high as +5. So entering this, there's what the vector field looks like when A is 1 and B is 1. Scaled down so all the vectors have the same length, right? It's not the true vector field. The true vector field, the arrows, as you move away from the origin here, would be much longer and gets so long that the picture just gets kind of messy. So we really are creating something called the direction field, where we rescaled all the vectors to have the same length. Though I believe Mathematica is making it so the colors correspond to the lengths. The more orangey yellow colors are longer vectors. The darker blue, purplish colors are shorter vectors. Technically, this vector field is also 0 when X and Y are 0, when the input is 0. So technically, there's also a trivial point, you might say, at the origin, which unfortunately VectorPlot doesn't plot automatically. So if we're going to actually see it, we need to do something extra. I'm putting the VectorPlot inside a show. And also with a comma, I'm going to put something else like listPlot is the simplest way to plot a point. In this case, it's the origin. And let's make it big. Not that points are big, right? Points have technically no area. But for emphasis, make a big dot at the origin to emphasize it's, well, in differential equations and linear algebra, we're going to call that an equilibrium point. It's a point that doesn't move. It's at equilibrium. Wait a minute. What's moving? What's moving is if you imagine the application here being fluid flow. You're imagining that those arrows are velocity vectors for water molecules, say, in a thin sheet of water. Like if you had two metal plates really, really close together, and you're able to get a thin layer of water in there, I don't know, 1 molecule wide? Is that possible? Probably not. Okay. I don't know, 1 micron wide, whatever, maybe a few water molecules fit in there up to down, but effectively it's two-dimensional. And you're looking at the flow, and what that's saying is all the water molecules are moving away from the origin. The origin is a source. It's like you've got a faucet there that's pouring the water molecules in, and they're moving away. And again, we don't see the length of the arrows there, but because the arrows get longer as you move away, if those are really velocity vectors, the molecules would actually be moving faster and faster the further they move from the origin. Probably not realistic, but you know, this is math, not physics, so we can pretend. In physics, in fluid mechanics, you have to worry about what's realistic and what's not realistic. But in math, we can pretend it's realistic. Okay? What happens as A and B change? If A changes but stays positive, gets bigger, say, watch the arrows, what's happening? They are changing. When A and B were both 1, the vectors were moving radially away from the origin, along rays from the origin. But here, when A is bigger than 1 and B is still 1, they're still moving away from the origin, but not radially. In the end, X heads to infinity, so to speak, if these were water molecules following these, faster than Y does. Unless you happen to be on the Y-axis, then X stays at 0. If A is positive but less than 1, it's kind of the other way, which can get even more extreme if B gets bigger. All right, what if I keep B at 1 but change A to -1, or to make it negative? Something like that can happen. Kind of like the origin is a saddle point in a sense. Water molecules are moving toward the origin in the horizontal direction, away from the origin in the vertical direction, and in between they're kind of doing like hyperbolic paths. And if A and B are both negative, then the origin is a sink. The arrows are all pointing toward it. But any way you slice it, no matter what A and B are, the curl is 0. Intuitively, people often say, well, I guess that means there's no curl to this vector field. There's no rotation. It's a little misleading because there's lots of vector fields that have a non-zero curl where you kind of look at the vector field and say, it doesn't really have any rotation involved. Shouldn't the curl be 0? So it's the wrong way to think about the curl. The curl is based on derivative values. And derivative values are always local information. Like for a function and its slopes, they're telling you slopes of tangent lines, which is telling you the behavior of the function near the point, locally, not globally. I mean, globally, the function could be going up and down all over the place. But near a point, it might have a positive slope. Near that point, it behaves like a straight line with a positive slope. Derivatives are always local information. Integrals are always global information. So this is a kind of derivative. It's only telling you there's no curling going on locally. That's hard to explain, though we will try, not today. Effectively, the book describes as, imagine putting a small cork in this fluid, in this two-dimensional sheet of fluid, maybe with some paddle wheels along the side so that it could start rotating if the water molecules cause it to start rotating. The fact that the curl is 0 means it actually won't start rotating. As another class of let's also look at the divergence here. What's the divergence for this vector field? D of f is the derivative of the first component with respect to the first variable plus the derivative of the second component with respect to the second variable. A plus b, not necessarily 0, unless b equals negative a. This is positive. In fact, how should I write it? If a plus b is positive, which would be equivalent to b being bigger than negative a. Is that the best way to write it? Maybe. 0 if b equals negative a, and negative if b is less than negative a. In particular, if a and b are both 1, what case is that? If a and b are both 1, then 1 is bigger than negative 1. The divergence would be positive. Why did I pick 1 and 1? Because that's the first situation here. A and b are both 1 here. The curl is 1. The divergence is 1 plus 1 is 2. Positive. What does it mean? Divergence is related to small regions and how much the fluid is going out of the small region compared to going in. Pretty obviously at the origin is a source. It seems like the fluid is going out of a small region near the origin compared to going in. But it's actually true near any point because the divergence is constant at 2. But it doesn't seem like that's the case. Why would more water be going in a small region than out of it? It's related to the lengths of the vectors, which are longer the further you are away from the origin than when you're closer. But you don't see it with this picture. They're slightly long. If you got a small region right about here, they're slightly longer on this side than they are on this side. So effectively, because of that, the velocity of the water molecules is bigger on the further away they are. So they're flowing out faster out of that side than they are flowing in on the other side. Is a basic intuition about why the divergence is positive in that case. If I switch to a case where b is less than negative a, I guess maybe where they have opposite signs or something. Like what if b were 2 and a were negative 1? What case would that be? If b were 2 and a were negative 1, that still would be this case. If b were 2 and a were negative 1, b were 2 and a is negative 1 to start off with, that's actually still a positive divergence. Yeah, the derivative a plus b would be positive 1. Still a positive divergence, even though the origin's a saddle point. A small region, the arrows pointing out would be, generally speaking, longer than the arrows pointing in. Or maybe there'd be more of them, so to speak, over a bigger area. I'm imagining a small disk near the origin.